Hey guys, welcome to another edition of Math with Matisich. We're going to be working out of your textbook today pretty much exclusively, and we are starting on page M1-26, M1-26. So our goal for the day is really to look at different expressions and compare if they are equivalent using graphs instead of only doing it algebraically like we did last week. So first thing that we need to figure out though is what type of a pattern do we have that formed here. So we've got another tiling situation. We've got Maureen and Matthew. Each one of these squares is equaling 1 square foot. So to describe the pattern, I think a good strategy that I've already shared with y'all is to create a table. So we've got this design number, and we've got some number of tiles here. So let's make a table then. I've got D for design number, and then I'll make my output here N for number of tiles. So with design number 1, looks like I've got 1, 2, 3, 4, 5 tiles. Design number 2, I've got the entrance and exit, and then this rectangle inside here, I've got 1, 2, 3, 4 by 2, so 8. So altogether, 10 tiles. Design number 3, so we've got a rectangle again. We go over 1, 2, 3, 4, 5, 1, 2, 3. So there'd be 15 tiles in there altogether. I've got an entrance and an exit. So I've got 17 tiles there. Again, that's for design 3. So in design number 4, what do y'all think that would look like? What's the pattern here? And then we can go about answering this, this question. What's the pattern? Is it linear, exponential, or quadratic? So anyhow, for design number 4, it's guaranteed that we're going to have an entrance and an exit. That never changed throughout the pattern. And it looks like every single time we had a rectangle that was connecting the entrance and exit. So try to come up with that. How many tiles would be inside of this rectangle? Pause the video if you want to and then check your work later. But it looks like this width here is increasing by 1 as we went along our designs. And then the length here was increasing by 1 as well. And we went from 1 in the rectangle to 2 to 3. So it looks like instead of being 1, 2, 3, 4, 5 by 1, 2, 3, it's probably going to end up being 6 by 4, which means we've got 24 tiles in here. And again, for the entrance and exit, we've got 1 here, 1 there. So 26 tiles altogether for design number 4. Okay, so for describing the pattern, let's check exponential first. Is there a constant multiplier that gives us from 5 to 10 to 17 to 26? So to check that, hey, 5 to 10, we will multiply by 2. And then 10 times 2 would be 20. It's not 17. So there is not a constant multiplier, which means this pattern is not exponential. So the natural thing to check next would be if it's linear. So let's look at the rate of change here. So to get from 5 to 10, we would go up by 5. To get from 10 to 17, you go up by 7. To get from 17 to 26, you're going up by 9. So it's very clear to you then that this is not constant. We're not going up by a constant amount. So your pattern is not linear. Okay, so the last thing to check would be, hey, is this quadratic? If you remember to check if a pattern is quadratic, you're looking at the second rate of change. So the change from 5 to 7 is 2. The change from 7 to 9 is also 2. So that's good. We definitely have a quadratic pattern. This one is quadratic. And then for explaining, how do you know that? The second change is constant. Awesome. Okay, so when you know that, keeping this pattern going should be a lot easier for you now. We know that the constant rate of change is going to be 2, or the second constant rate of change is 2. So instead of going up by 9, you'd end up going up by 11 to make this still constant, like I said, right? So design 5, then you would have 26 plus 11, which gives you 37 tiles. Okay, so that answers the first question. Let's move on. Let me get some of this stuff out of the way and go to number 2. So Maureen did something She created an expression for this. Hers is a little bit convoluted and kind of confusing, but she's subtracting, even though we're adding tiles each time. So I think the strategy that she did was, all right, so let's look at design one. I'm just going to redraw it. So we had our entrance, and then we had this really slim, narrow rectangle, like that. Just pretend those boxes are all the same. And then her exit. So since she's squared right here, she's actually kind of like pretending, I guess, that she's starting off with a square. So she's pretending that there's this square that kind of overlaps everything. Okay. So like for design number 1, 1 plus 2 is 3, 3 squared is 9. So she's got 9 square tiles there, right? She's got 9 tiles all together, and then she's subtracting these pieces that she added. This piece, this piece, this piece, and this piece. She's subtracting 2 times the number of tiles that she added. So one set of tiles here, the other set of tiles there is representing this thing, this part. And then what would she be left with is just these purple tiles, which is what we were wanting. So it looks like that definitely that would work. It's just kind of a roundabout way of doing it. Okay, so let's continue on then. She turned it into a whole square, which is cool, but not something I'm concerned with. So Matthew just created a standard quadratic expression, n squared plus 2n plus 2. So what we're going to want to do is use technology to verify graphically the equivalence of these two expressions. So let's go to a graph. Maureen's expression was n plus 1 squared minus 2 times n plus 1, those tiles that she was adding. Well, let's actually change n to x. This calculator will like that a lot more. The other guy, his name is Matthew, he just said x squared plus 2x plus 2, which represents those corners. Looks like I didn't get something right, so let me go figure out what her expression was. N plus 2 squared. 2 there. Okay. Anyhow, this website too, if you ever want to go here on your student laptops, you can get there. It's just desmos.com, desmos.com, and it's got an awesome graphing calculator that you can use. So we see Matthew's expression in the green, Maureen's expression in the red, and notice that they are overlapping perfectly. It doesn't matter how far I zoom out, they're always directly on top of each other. And that proves equivalence. If 2 graphs line up perfectly like that, the expressions are equivalent. Okay, so let's go back. We did that. We described that they are equivalent graphically. Identify the parts of the graph. Well, we've got a square. We're adding 2 tiles, a constant 2 amount of tiles for his entrance and his exit. Not a big deal there. I do want to go to this part though. So verify the equivalence of the 2 expressions algebraically. This is something that I definitely want to do to make sure that we know or recap some of the information that we covered last week. So Matthew's expression was x squared or n squared. It was just a different variable plus 2n or 2x plus 2. So I'll do the same thing for Maria, and I'll just use x instead of n. So she had x plus 2 squared plus 2 times x plus 1. Not plus, minus, sorry. She was subtracting those tiles that she added because she made the whole square right here. Minus 2 times x plus 1. Okay, so Matthew's expression, like that, is already simplified in general form. We don't really need to do anything to that. No parentheses to get rid of. But we can simplify this expression, x plus 2 squared. Be careful here. It's not just the x or the 2 that's being squared, being multiplied by itself. It's this whole expression. So how you would rewrite this is x plus 2 times x plus 2. Then over here, we've got some pretty simple distribution to take care of. The negative 2 is being multiplied by this and this. Negative 2 times x, and then negative 2 times 1. Negative 2 times x is negative 2x. Negative 2 times 1 is negative 2. Okay, so to get rid of this, we're doing double distribution. The x gets distributed to everything over here, like that. And also the 2. Double distribution. We're distributing two things to two terms. So x times x is x squared. X times 2 is 2x. 2 times x is also 2x. And then 2 times 2, I don't know why I put a 4 there, not an x. 2 times 2 is 4. And we still need to include this in her expression as well, negative 2x minus 2. Okay, at this point, we just need to combine like terms. So like terms are the same variable to the same exponent. So like x squared, there's no other x squared term here. So it's just gonna be x squared, nothing to combine it with. Now the x terms, anything with an x on it, x with no variable or no exponent, 2x, 2x, negative 2x. 2x plus 2x is 4x, minus 2x, 2x. So I just combined 2x, 2x, and negative 2x. And then we can also combine some constants. I've gotten rid of my x squared. I've gotten rid of my single x terms. All that's left is 4 and negative 2, which becomes positive 2. So you should have enough information now to answer this question. X squared plus 2x plus 2 is algebraically equivalent to x squared plus 2x plus 2. That's why these two things, or the two graphs, went on top of each other. They definitely are equivalent. It's a good thing. Okay, so our last question is, to accommodate outdoor furniture, a grill, and a shed, the patio must have an area of at least 125 square feet, not including the walkways. What is the smallest design they could build and still have enough space for these items? So going back to your table, remember I like design 4, we had, I think, 37 tiles. So one easy way that you can answer this is to actually go back to that graph. Let me clear this stuff out of the way. So again, this graph, I need 125 tiles. So I'll go all the way up here to 125, which is right here. So it looks like design number 10 would not actually fit what they needed. Design 10 would only give you, where are we at here? Design number 10 would give you, I don't know, about 122 tiles or so, and we needed at least 125. So the smallest design would be, okay, go like this and make it a little bit easier to clear. We need to get here. We need at least 125 tiles. That's design 10.136, but we're gonna actually go up from that and use design number 11. Design number 11 would do this for you. Design number 11 has at least 125 square feet, so it would include all of those tiles that they needed for their grill, shed, furniture, whatever else. That's actually gonna do it for this video. I think the most important thing is just know that if you prove things algebraically equivalent, their two graphs will be directly on top of each other. No deviations from that. They're gonna be directly on top of each other. And that's really it. So hey guys, thanks for watching. You'll have an assignment here, a little bit to do. Good luck on that. And of course, just if you have any questions, send me an email, stop by office hours or whatever. All right guys, bye-bye.